Okay, so we're going to start our aldolase protein purification experiment. And in this experiment, we're going to have 50 grams of minced chicken, freshest chicken possible, never been frozen, so that all the proteins are in very good shape. And it's minced with little razor blades to get it into very small pieces. It's weighed out so that we have approximately 50 grams. The exact number does not matter. In this case, I think it's 52 grams. So whatever your number of grams, you're doing 3 times the volume of our homogenization buffer. And in our homogenization buffer, it's a phosphate buffer, because that's going to give us the pH we want. And we have beta-mercaptoethanol in here. And as I told you in the lecture, beta-mercaptoethanol will keep the proteins in a slightly reducing environment, so the number of disulfide bonds does not change. Also, there's some EDTA in here, and you'll recall from previous lectures that EDTA is needed to chelate those divalent cations, so proteases do not have activity. So you simply pour your buffer, your nice cold buffer, into the blender. And just like we've done previously, we're going to blend. Four individual blendings, 15 seconds each on the blender. At the end of that period of time, you're going to pour your protein material into a GSA tube. Now remember, in this, there are whole cells, there is connective tissue, there is protein, there are quite a few things in here. So what we're going to do next is we're going to be spinning it in a centrifuge, a GSA centrifuge, because this is a GSA bottle. And we're going to be spinning it at 4,000 RPM for 5 minutes. When you see us next, we will have already spun it and we'll be pouring off the supernatant. So this is your bottle that has come down from the centrifuge. Notice the very large pellet. That differential centrifugation separates all the connective tissues, the whole cells, all the very large material. So now you're going to pour it through mirror cloth into a funnel. So you're going to try to get as much as you can out of here. If you happen to get some of the solid material, it's not the end of the world. We're going to be squeezing our bag, but it is a very soft, loose pellet. So don't be alarmed if some of it goes plunking down into the funnel. So you have the funnel on top of a graduated cylinder. And when you're finished, you can just sort of squeeze it out to make sure you've got the maximum yield possible. So then it's in a graduated cylinder, so you can take a sample of it. So you want to make sure to take a 1 ml sample of this before you add the ammonium sulfate to it. Okay, so one of the other things that you're going to be doing as a group when you are busy doing the ammonium sulfate fractionation of your aldolase, one person in your group can be working on that while another person is working on pouring the gel equilibration column. So remember, the gel equilibration column simply separates things based on what size they are. So your protein's not going to stick to a column at all. It's simply going to run through a column based on the size of it. So to be able to pour this column, you will be given a bottle of cephorose beads, and you will need to pour those beads into a column. And you will be packing the column by doing this. So basically, you're going to pour beads into the column. You can pour more than you need. You can pour up to here, for example, and let the liquid flow through the column. So all of that buffer that the beads are currently suspended in is going to be flowing down, and as it flows down, the column will be packing higher and higher. So on the first day when you're working with this column, you're going to just make sure you keep loading material into here until the packed height of the column is right below the level of this colored top of the column. So you must have the top of the column right here, just a little bit below. And that's because when you're loading things into the column, you need to be able to see where the end of your pipette tip is. And if you have your pipette tip, if you have the column up here, you won't be able to see if you're up here where the pipette tip is, but it's glass down here. So if the level of your column is right here, you will have the level of your tip right here, and you'll be able to see exactly where your tip is. Now you have to have the column at that level. You have to be able to see the tip, because you need to be able to accurately load in a very, very small area your samples onto the column. So this is basically just showing you how it's going to drip through, how you're going to pack, how you're going to keep track. The number one rule when doing one of these columns is never ever let the column run dry. So you always want to make sure you have gel exclusion equilibration buffer. As you are packing the column, if you get a little low on buffer here, but you think you have maybe enough beads in here, add some gel equilibration buffer to keep packing it. After the column is packed, you're going to be adding around 2 column volumes of gel equilibration buffer to make sure that you've rinsed everything through and it's now equilibrated in the buffer that we're going to use. How are you going to know what a column volume is? Well, if you turn off the stopcock and you pour water in here up to the level that you want it, want your column to be, and then you pour the water into a graduated cylinder, you'll know the volume of that water. So that's how you're going to find a column volume. If you don't have a graduated cylinder, you can do some complicated measurements and, you know, the volume of the cylinder times the height, stuff like that. But trust me, a graduated cylinder is a heck of a lot easier. Your next instruction here is in the protocol, step 4 and 5A, and we're not going to be doing step 4 and 5A because it's been shown that DNA is not a problem in this procedure, so we don't have to worry about adding DNase to it. So we're going to pick up this procedure with determining how much ammonium sulfate it takes to make our solution 40%. So basically, what we have here is an ammonium sulfate table. We have no ammonium sulfate in it currently. We want to bring it up to 40% ammonium sulfate, which is 243 grams per liter. But we do not have an entire liter. Instead, we have about 61 mils in the graduated cylinder. So 61 mils times 243 grams per liter is 14.82 grams of ammonium sulfate. So you're going to weigh out your ammonium sulfate, making sure to do it carefully on the balance. And you're going to take a double beaker system. Now, when you do this, you're going to have ice in between these 2 layers right here. I don't have ice in here because I wanted you to see what's happening, but it's very important for you to have ice in here. And there's a little stir bar in the center. Remember to take a 1 ml sample first. You're going to need it later. So you're going to add your solution in there. And you're going to start stirring on the stir plate, making sure your stir bar is really moving everything around. And then you're going to slowly add your ammonium sulfate. And again, you're going to have ice in between these 2 layers, so you will not be able to look through here and see what's going on. But you're going to add the ammonium sulfate slowly over a 5-minute period. You want to avoid a locally high concentration of the ammonium sulfate. A locally high concentration means that you're going to have too much ammonium sulfate because it's going to take a time to dissolve. It's not all going to dissolve immediately. So if you have a bunch just sitting on the bottom waiting to dissolve, your proteins that are next to that solid ammonium sulfate waiting to dissolve are potentially going to be higher than 40%, and you do not want that to happen. So you want to allow lots of time for it to dissolve while you're adding it. If it takes you less than 5 minutes to add this, you're adding it too fast. So that's a good benchmark. So you want to make sure you have it coming in here over a 5-minute period. When the 5-minute period is over and all the ammonium sulfate has been added and you've checked to make sure that it's dissolved in the bottom, then you're going to put it into SS34 tubes. And remember, SS34 tubes are the ones that don't have the top, that have the round bottom on them. And we're just going to pour it into equal numbers of SS34 tubes, maybe 2 tubes, maybe 4 tubes. It's going to depend on your particular volume. So if you have a larger volume than I did with 60 mils, then maybe you'd need 4 tubes. But generally, probably most of you will only need 2 of the SS34 tubes. So each SS34 tube cannot be filled all the way to the top because they don't have lids on them and because you're putting them into an angled centrifuge rotor. So you want to make sure that you only have each tube around 2/3 filled. So if you can't fill them about 2/3 by doing it in 2 different tubes, then you're going to have 4 tubes. But most of you will probably be able to do it in 2 tubes. So we're going to pick this up again after we have spun it, after we have added the ammonium sulfate, after we have allowed it to dissolve, after we have poured it into the SS34 tubes, after we have spun it in the SS34 tubes at 14,000 RPM for 10 minutes to allow all that protein that's now precipitated out due to the ammonium sulfate, forcing it to come out of solution. After all that has pelleted out, our aldolase is still going to be in solution. What we are pelleting out is proteins other than our aldolase. And what we're going to do after this, we're going to bring it to a higher concentration of ammonium sulfate. And at that higher concentration of ammonium sulfate, now our aldolase will be in the pellet. And when it's in the pellet, then we'll be able to resuspend the pellet and do dialysis on it.